Okay, so we learned two basic decision rules based on the p-value and the t-statistic. So the idea is we have the sample average test statistic and standardize the sample average into t-statistic and process the t-statistic into p-value and compare to significance level, right? But if you are lazy or if you want to change the decision rule, instead of transferring the t-statistic into p-value, you bring the significance level to the second level, right? So significance level was compared to p-value, but now bring it up. What I'm going to do it here is now you don't even standardize the sample average and directly make the decision based on the sample average. So you don't process anything here, but bring the significance level to this level. So that is the third decision rule we are going to study here. Idea is also simple. Basically, if X bar is too much different from your belief, you are going to reject the null hypothesis. Exactly this is the idea of hypothesis testing. And then, how close is close enough? How close is close enough and how different is too different? We are going to use this form. So, if X bar is within plus minus m away from mu 0, right? Then we will not reject the null hypothesis. And then we are going to think your belief is consistent with the data. So these two cutoffs are critical values, right? So mu 0, belief minus m, belief plus m's are called critical values, right? Upper critical value, lower critical value. And we call this interval plus minus m around mu 0 is called the acceptance region because we accept the null hypothesis if the sample average belongs to that region. But outside the region is the rejection region because the null hypothesis is rejected. Okay? So the idea is like this. So my belief is 30, but I allow certain buffer around 30. So I choose critical values here and here, and then you reject any number, any sample average that is below this point or above this point, right? Because they are away from too much different from your belief 30. Okay? So this is intuitive. And then the problem is how to calculate this m, how much buffer we need to accept our null hypothesis. That depends on the significance level again. So basically the three decision rules are consistent, should be consistent with each other. So we have to convert that from the decision rule from t-statistic, right? So basically, this is the t-statistics decision rule. The null hypothesis is accepted, not rejected, if the standardized difference is smaller than lowercase z alpha over 2. So then what you do is you have to undo the standardization. So the difference between t-statistic and the sample average is the standardization process. Then do the standardization the other way. Cancel out the standardization. So put it this way. After standardization, this is when your null hypothesis is not rejected. If the standardized t-statistic is in between plus minus z alpha over 2. Now what I'm going to do is move the standard deviation away and plus mu 0 all the terms to isolate x bar in the middle. So simple algebra, you can obtain x bar remains in the middle and the left hand side becomes mu 0 minus something and on the right hand side mu 0 plus something. Exactly this is what we wanted. This much is m. We needed. Excuse me. So if you choose critical values like these, that will be the consistent decision rules as the p-value or the t-statistic. So then you don't need to worry about calculating p-value. Okay, so formula, upper critical value, lower critical value, based on this formula. And you know, this is familiar form, and you know, like I will discuss that later. So based on, once you calculate the critical values, you are going to compare that to the sample average, right? So once you calculate the sample average, you don't need to do anything on the sample average. Sample average remains the same, but the other side, its comparison counterpart, is manufactured, okay? Manipulated to the critical value. So, and in other words, if your sample average is within this much distance, then your belief is okay. So if your belief is within the neighbor of the sample average, you are good. That is the idea. And here is the comparison. Confidence interval takes this form. Critical values take this form. The only difference here is x bar and mu 0. But it clearly explains the different background. Say, confidence interval is to find where mu is. We are wondering where the true mean is. So, and what we have is the data. So we start from the data. Given the data, it looks like the mean is x bar. But we are uncertain, so we are going to include margin of error around it, right? So we believe the true parameter is lies between these 2 points. That is our idea, right? It is estimation. However, in the hypothesis testing, we start from our belief. So starting point is different. I have a strong belief of mu 0. I believe that my mean is like the true mean is mu 0. But then where the sample average would be? If my belief is correct, the sample average would be around this much distance, within that much distance. So if the sample average belongs to this interval, then your belief is correct. So that's how you interpret these two similar formulas. They are different, similar, but it's the comparison between these two. It's I think the best way to explain the philosophical difference between estimation and hypothesis testing. That's the difference. And by the way, what is confusing? I'm really confused a lot. In confidence interval, we call 1 minus alpha as the confidence level. So this is the probability of correctly estimating the true parameter. But in hypothesis testing, we call alpha as the significance level, not 1 minus alpha. So sometimes, we have to say the confidence level is 95%. But that is the correct way. But sometimes I may say our confidence level is 5%, right? Then either I meant 5% is our significance level, or our confidence level is 95%. So, but anyhow, given the context, you know what I'm saying. So please pardon my confusion. It's not that critical, okay? And now let me compare the critical value approach with p-value and t-statistic. So the major difference is like this. P-value and t-statistic did not depend on the significance level, alpha. And you only need data to calculate them. You only need data and belief to calculate the p-value and t-statistic, okay? However, when you use critical value approach, critical value does not depend on your sample average. It depends on your belief and your significance level. So when you change the significance level, your critical value changes. Okay, that is a big thing. So when I explain p-value and t-statistic, what I said is when you have data, but if you may change alpha, given the same data, you want to change alpha from here and there, then p-value approach or t-stat approach is good, because once you calculate them, just you can change alpha easily. However, like now think about this. You have the same decision rule, but what changes is the data, right? Suppose that you apply the same decision rule to this group and that group with the same alpha, same decision rule, then critical value may be more convenient, because once you define the critical value, you can apply that to this group, sample mean, calculate sample mean from that group and compare that to the critical value, and use the same critical value to another group, and another group may have different sample mean, but the standard is the same. Decision rule is based on the same critical value. So if you repeat the hypothesis testing to different data, critical value is more convenient. So we are going to do exercise about that in the next chapter. So you are going to use critical values a lot in the next chapter. And now let's think about what happens when alpha changes. As I said, idea is same. When alpha increases, you are going to reject your belief more often. So that means rejection region should expand and the acceptance region should shrink. That means the critical values move closer to mu zero, or the margin should decrease. Margin will decrease so that you are more strict, right? You are more rejecting the null hypothesis. And let's think about the standard error. Standard error is the randomness in your test statistic, right? So this standard error is the standard deviation of x bar. If the standard error increases, that means there are more uncertainty, more noise in the data. So that means you have to allow larger margin. The intuition is equivalent to the confidence interval. You need larger margin, so your critical values will be wider. That is intuitively understood. Okay, let me think about an example. So we will consider I-beams. Like this is a steel beam used in construction to make building, right? And suppose that the smallest I-beams, standardized I-beam, must be 80 millimeter tall in this dimension, right? So it must be 80 millimeters tall. So what I'm going to do is I'm going to inspect I-beams and check if the mean of the I-beam is 80 millimeters. The height of the I-beams are correctly sized. So I will set up the null hypothesis this way. So I believe all the I-beams are correctly sized. That is my null hypothesis. Without evidence, I'm the inspector, and without evidence, I cannot punish the manufacturers, right? So I'm looking for evidence to punish the manufacturers who are cheating, right? Who are making wrong-sized I-beams, which can be very dangerous for safety. Okay, so and then as an example, I'm going to consider 400 sample of I-beams, and I calculated their mean height. I measured their height, and it was 79 millimeters. And the standard deviation is 10 millimeters. So it is 1 millimeter shorter than the standard. But it could be the 1 millimeter could be measurement error or recording error. When I record, like I may mistake like 0 as 6, something like that. So, and then how can we make the decision? So I will do some exercise. So throughout this exercises, pause the video when needed. Okay. First, find the t-statistic. If you don't remember what the formula for the t-statistic, you may go back to the previous slides. And it should be simple. Calculate the t-statistic here. Okay, so the answer is like this. So your sample average is 79, and your belief is 80. So the difference is -1. Numerator is the difference, and you standardize that with the standard error. Divide by standard error. Sample size was 400, whose square root is 20, and standard deviation is 10. So we have -2. After standardization, the 1 millimeter difference becomes -2 in the scale of standard normal distribution, right? And now, suppose that the significance level is 1%. Then, when can you reject the null hypothesis based on the t-statistic? So, you choose the decision rule. Okay, when you reject, you are going to reject only when the difference is large. So the inequality must be in this direction. So A and C are crossed out. A and C are conditions to accept the null hypothesis. And then the number depends on 1%. And 1% is the smallest among the common choices. So the outside probability is only 1%. That means it must be wider. The cutoff must be large. So the answer is E. You may go to a previous slide to see the number. But anyhow, so the lowercase z for 0.5% equals 2.58. So this is a common choice number. And then, think about this. So we obtain t-stat -2, and our threshold is 2.58. Then do you reject or not? In our example, given the data, example data, can you reject the null or not? So our threshold is 2.58. What this means, if the standardized difference is greater than plus or minus 2.58, you are going to reject. But our standardized difference is only -2, which is within this buffer cutoff. So you are not rejecting the null hypothesis. The answer is no. So that is how we compare. So we set a plus minus 2.58 as the cutoff, but your observation is -2. So within the interval, so you are good. Your difference is small enough. Okay. So then I'm asking you, what happens if you increase the significance level to 10%? Okay, so when you increase alpha, you have to change this number. Plus minus the threshold, plus minus 2.58 must become plus minus 1.64, right? Now you are narrowing down the allowed margin for error. So now it is plus minus 6.4, and your observation is -2, which is outside of the threshold. So you have to reject the null hypothesis. Your difference is larger than what you are allowing for. So you reject. Okay, this is the t-statistic approach. Now let's compare that to p-value. So calculate the p-value. What is the p-value in this case? Remember, t-stat is -2. So based on the t-stat, calculate the p-value. Okay, the answer is we are looking for the probability outside plus minus 2 in the standard normal distribution. So in the standard normal distribution, you calculate probability smaller than -2, greater than 2, and we know they are the same probabilities. So calculate only one of them. And repeat the same probability. It is 4.55. So given this p-value, find all significance levels at which H0 is rejected. at which the null hypothesis is rejected. So among these three common choices, when can we reject the null hypothesis? Okay, this is easy if you remember that the rejection happens when p-value is smaller than the significance level. So p-value is already 4.5%. So if the significance level is greater than that, then you are rejecting. So the answer is D. 5% or 10% are greater than them. So in other words, in these two, under these two significance levels, the p-value is too small. So you have to reject the null hypothesis. Okay. So this is the last question in this video. Now try to find the critical values for 1% significance level. I will come back with continue the example. So please do the algebra while you move on to the next video. Thanks. See you in the next video.